Hello, students, and a very warm welcome. Today, we're going to look at a very important topic in organic chemistry, the preparation of amines.
Let's start with something you might have seen in your school lab. Imagine a flask with a vibrant red-orange chemical inside, and as you watch, it slowly turns completely colorless. What is happening? Is it some kind of magic? No, not at all. It's pure chemistry. And this simple observation is the key to unlocking today's entire topic.
So why should we care about this? Well, this is not just about memorizing reactions for an exam. This is about learning how to be a molecular architect. You see, preparing amines allows us to design and build essential molecules, like medicines and dyes, from much simpler, easily available starting materials.
To build anything, you need two things, right? Raw materials and the right tools. Well, in chemistry, it's exactly the same. So let's open our chemical toolkit and have a look at the core idea.
Okay, so what's the basic idea? It's actually very simple. We take a compound that already contains nitrogen, but it's not the amine we want. Then, we use a very specific chemical tool to transform it into the amine we need. It's a process of conversion, taking one thing and skillfully changing it into another.
So what are these raw materials I'm talking about? Well, think of them as different types of building blocks we have in our workshop. First, we have nitriles. Then, there are amides, and finally, we have nitro compounds. Each of these can be our starting point to build an amine.
And what about our tool, the master tool, that works on all these different starting materials? Well, that tool is a process called reduction. Now, don't let the word scare you. Reduction simply means adding electrons or adding hydrogen atoms to a molecule. That's all there is to it.
So what's really going on at the molecular level? You see, in our starting material, the nitrogen atom is in what we call a high oxidation state. Think of it like this. The nitrogen is a bit poor. It's missing some electrons. Our tool, the reducing agent, is like a good friend that comes along and gives electrons to the nitrogen. This simple act of giving electrons fundamentally changes the nitrogen, converting it into its final amine form.
Now, to make sure this idea sticks in your head forever, I want to share a very powerful analogy with you. This will make the whole process feel much simpler. Let's see how this works.
I want you to imagine a sculptor in their workshop. The sculptor starts with a rough block of stone, right? Well, that stone is our starting material, the nitrile or the amide or the nitro compound. Now, the sculptor takes their chisel and hammer to carve the stone. That chisel is our reducing agent like lithium aluminum hydride or tin and HCl. And what happens when the sculptor finishes? They have created a beautiful, finished statue. That statue, that's our final amine molecule.
So why does this whole concept even exist? Well, it solves a fundamental problem for chemists. The problem is this: how can we build complex and useful amines when we only have simple, common starting materials available? The answer to that problem is reduction. Without these methods, we simply could not make the huge variety of amines that are needed for medicines and industries today.
Okay, let's create a mental picture of this whole journey. Just picture this. At the start, our nitrogen atom is trapped in a high-energy, high-oxidation state, stuck inside a nitrile or a nitro group. Then along comes our tool, the reducing agent, which adds electrons. And finally, what do we see? We see the nitrogen atom is now freed. It has settled into its stable, low-oxidation state as the final amine. So it's a journey from trapped to free.
All right, we have the core idea, and we have our sculptor analogy. Now for the really interesting part. Let's see how this sculpting of molecules is used, not just in our textbooks, but in the real world.
Do you remember the question I asked you at the very beginning of this session about that red-orange liquid that becomes colorless? Well, that is a real reaction. It's the reduction of nitrobenzene. That color change you see with your own eyes is the visible proof that reduction is happening.
So let's break down what you are seeing. The red-orange nitrobenzene, that's our starting block of stone. The mixture of tin and HCl, that's our chisel and hammer, a reducing agent. As the reaction proceeds, the color fades away. That is the visual signal that the nitro group is being transformed, it's being reduced. And what is our finished statue? It is a colorless, oily layer of a new molecule called aniline.
And please remember, this is not just some small experiment we do in a school lab. This exact same reaction is a cornerstone of the chemical industry. It is scaled up in giant reactors to produce thousands of tons of aniline. And that aniline is then used to make all sorts of important things, from the dye in your glue genes to critical medicines.
So, let's do a very short recap. If you forget everything else, just remember these three things: Number 1, the core idea. We make amines by the reduction of other nitrogen compounds. Number 2, the mental image. Think of a sculptor using a chisel to carve a statue. And number 3, one real example, the industrial production of aniline from nitrobenzene. That's it.
I want to leave you with this one thought. Don't just try to memorize reactions. Try to understand the story behind them. If you can just remember the core idea, that one mental picture of the sculptor, and that one real example of aniline, I can promise you this topic will feel so much lighter and so much easier in your exam. Keep learning. Thank you.